All right, welcome back, fellow chemists. We're going to be wrapping things up with our solutions unit. We're going to be talking a little bit about what we call colligative properties. Okay, so as you can see here, colligative property is a property of a solution that depends on the total number of solute particles, but not their identity. So it doesn't matter what the solute is that I'm dissolving in there. The only thing that matters is how many particles I'm dissolving in there. And I'll show you what I mean here in a little bit. Okay, now there's several different colligative properties that we can talk about, but we're going to focus on two of them. We're going to focus on the boiling point elevation and the freezing point depression. Okay, so whenever I add a solute to a solvent, right, I'm going to raise the boiling point and I'm going to lower the freezing point, right? Hence why it's called boiling point elevation, freezing point depression. Okay, so always happens for your solution. Always boiling point goes up, freezing point goes down. Okay, so let's, for example, take a look at water, right? Water is our universal solvent. We use that most often in chemistry to dissolve things. Okay, so the boiling point of pure water, if you don't recall, that is 100 degrees Celsius. The freezing point is 0 degrees Celsius. All right, so if I draw a picture of a thermometer over here, okay, there's my thermometer. Water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. Okay, so what we can do, oops, it erased my 0 there. Okay, if I add a solute in here, okay, now we're essentially going to be increasing the temperature that it boils at. So let's say maybe it increases up to 110 degrees. Okay? It's also going to lower the temperature that freezes at. Right? Let's say it lowers it down to, say, -5 degrees. So now, here, this is going to be my solution. Okay, so my solution now freezes at -5 and boils at 110. Okay, and again, it doesn't matter what the solute is that we're using. The only thing that really matters is how many particles are going to be dissolved in there. Okay, so probably the best place that you've seen this in action is taking a look at freezing point depression, putting salt on the roads. All right, at this time of year, things start getting colder. If you get really cold, you start getting ice to form, right, on the roads and on the sidewalks, right? And to combat that, a lot of people will spread salt out, right? And the reason for that, why that works, is as the salt starts to dissolve, it makes a solution with the ice. Okay, and as it makes that solution, it starts to lower the freezing point. Okay, so let's say that the temperature outside, I'll use pink for the temperature outside. Let's say it's pretty cold, below 0 Celsius. It's at -2 degrees. All right, let's say that when you throw the ice, salt on the ice, what happens is it lowers that freezing point or that melting point down to -5. So now the temperature is only -2 degrees outside. It melts at -5 or freezes at -5 degrees. Okay, so now that ice that was there, right, it froze when it was originally at 0. Okay, now we're saying in order for it to stay frozen, it has to get to -5 degrees outside. Okay, so when it's only -2, that means we're going to see that ice start to melt, right? And if it gets really cold outside, like one of those polar vortexes comes through, right, then it starts to get to a point where no amount of salt that you throw out there is going to melt that ice because it just gets too cold. Right? If it gets down to, say, something like -10 degrees below 0, okay, that ice, that water is still going to freeze at -5, and if we keep throwing more and more salt on there, there's a limit to how much will dissolve, right? It'll become saturated. Okay, so there's only so far that we can lower that freezing point, right? So there's only going to be a certain temperature that this is going to work out for. Okay, but what's happening is those solute particles are helping to lower that freezing point. Okay, so instead of water freezing at 0, it's going to freeze now at -5. Okay, and that's going to help to melt any ice that's already been formed there. Right, it makes it safer for us to go driving and walking out. Okay, so what we want to be able to do is we want to look at various different solutes, and we want to be able to say, which one is going to give us the highest boiling point, which is going to give us the lowest freezing point, etc. Okay, so before we can do that, though, we have to talk about something we call the Van Hoff factor, or this I value. Okay, so remember, when ionic substances break up, when they dissolve, they will break up or dissociate. Okay, and when they dissociate, they can break up into multiple particles. Right, and that's what this I is measuring, is how many particles does the solute break up into when it dissolves. Okay, so let's take a look here at some of these examples. Okay, so to start off with, I've got lithium chloride. Right, when lithium chloride dissolves, that's going to break up into lithium ions. Right, I'll put the AQ here, and chloride ions. Okay, so I'm breaking up into 2 ions. So I started off with one thing, and I'm breaking it up into 2 things. So my I value here, that Van Hoff factor, because I break up into 2 ions, my I value is 2. Okay, if I come back over here to calcium chloride, the next one. Right, I've got calcium and chloride. So I've got calcium with that +2 charge. Right, and I've still got chlorine. Chlorine is still Cl-. Okay, but now I have 2 of them here. Right, so I'm not going to do a 2 like this. Right, because Cl-, that is the ion that chlorine makes, right? Cl with a -1 charge. But now I have 2 of them. Okay, so now I've got 1 calcium and 2 chlorines. Right, so my I value here, I've got 3 total particles that it's broken up into. Okay, why don't you pause the video, try out the next 2, see what you come up with for those, and then let's compare our I values when you're done. Okay, so let's take a look here at aluminum chloride. Okay, so aluminum, I'm going to break that up. I get Al3+. Okay, and then we are still making the same chloride ion. Okay, but this time I've got 3 of them in here. So I'm going to do 3. So I've got 1 aluminum and 3 chlorides. So my I value is going to be 4. All right, next up, I've got magnesium nitride. Okay, when this one breaks up, I'm going to break it up into Mg2+, okay, and N3-. Okay, but going back over, I've got 3 magnesiums and 2 nitrogens. So I'm going to have to do 3 magnesiums, 2 nitrogens, so 3 + 2, that's going to give me a I value of 5. Right, and the last one, this is a trickier one. Okay, because if we look at these, let's look at the type of bonding that we have. Okay, lithium chloride, calcium chloride, aluminum chloride, and magnesium nitrate. These are all ionic. Okay, C6H12O6, those are all non-metals. Okay, so this guy down here, this is covalent. Right? If you remember, when we talked about dissociation, ionic substances will break up into their ions. Covalent stays together. So this guy, when it dissolves, it's going to stay C6H12O6. And I'm just going to use that AQ to show that now it's dissolved. Okay, so this guy, it stays together. So there's only one particle here. So my Van 't Hoff factor, my I, is just 1. Okay, so ionic substances break up into their component ions. Right? Covalent do not break up. Right? They just dissolve. They go from solid to aqueous. Okay, so why is this important? Right? Remember we said with colligative properties, it's not the identity of the particles. So it doesn't matter that it's lithium chloride, calcium chloride, or whatever. What matters is how many particles. Okay, so the more particles it breaks up into, the higher the boiling point becomes, the lower the freezing point becomes, right? So the greater the difference. Okay, so what we might see here is something like question 5.6. Okay, using those substances above, okay, list the following solutions and pure water in order of increasing boiling point. Okay, so remember, as my number of particles increase, right, my boiling point also increases. Right, that's a semicolon in between there. Okay, so as the number of particles increases, my boiling point increases. Okay, if I have just pure water, right, pure water is going to have the lowest boiling point because I haven't added anything to it, so the boiling point's not going up. Okay, so then I'm just going to put these in order. I'm going to look at those I values over here, okay, and I'm just going to put them in order from the lowest to the greatest. Okay, so my next one is going to be the C6H12O6 because it has an I of 1, right? And then I'm going to have my lithium chloride because I of 2. I of 3 was the calcium chloride. I of 4 was the aluminum chloride. And finally, magnesium nitride. Right, that one has an I value of 5, so it's going to have the highest boiling point. Okay? Let's take a look at the last one here, using the equations above. Right, so again, the same information we had. List the following solutions in pure water in order of decreasing freezing point. Okay, so key here is we're decreasing. Okay, so remember, as my number of particles increases, right, my freezing point decreases, right? The freezing point goes down with more particles. Okay, so if we're paying attention here, we're going to follow that same order that we were up here. So let me copy that, and I'm just going to paste down here. Okay, so pure water is going to have the highest freezing point, and then as I add or increase that I factor, right, the freezing point is going to decrease more and more and more. So the lowest freezing point is going to be over here at the MG, that should be a G there. Got my G in magnesium. Okay, Mg3N2. Okay, so pay attention to the wording on here. Right? If it had said in order of increasing freezing point, the order is going to be the same, just it's going to be flipped, right? Because magnesium has the lowest freezing point, or so the magnesium nitride has the lowest freezing point, And then as I decrease that I value, okay, then my freezing point is going to be increasing. So lastly, right, just to reiterate, okay, my I value, pure water, we can think of that as an I value of 0 because there's nothing breaking up there. It's just pure water. Okay, the sugar, C6H12O6, it's covalent, so it's an I value of 1. Right, then 2, then 3, then 4, then 5. Okay, so I'm just putting them in order of how big their I value is.